As shown in a previous video, the central limit theorem has real value in making estimates of the population mean from a small sample. It is, however, limited by the fact that it requires the standard deviation sigma of the population to be known. In 1908, W.S. Gossett discovered a new distribution by using the standard deviation of the sample S to approximate the sigma of the population. Mr. Gossett called the new distribution the student's t distribution. The name results from the fact that Mr. Gossett's employer at the time did not want this research published, so he published it under the name student's t distribution, and the name has remained in his honor. The variable t is calculated using this equation, and has a similarity to the equation we used to calculate the z-score in the previous videos. The very important difference is that instead of using sigma, the standard deviation of the population, it uses s, the standard deviation of the sample. The variable t should be thought of as serving the same purpose as z when the standard deviation of the population is unknown. Let's now look at the difference between the standard normal distribution and the student's t distribution graphically and note some differences. First, let's recall that the standard normal distribution has a mean of 0 and a standard deviation of 1. The value along the horizontal axis is the z-score, the relative standing. Also remember that the cumulative frequency of the standard normal distribution always approaches 1 as the value of z becomes much greater than 0. The student's t distribution has a very similar shape. The values on the horizontal axis now represent the variable t. The cumulative distribution of the student's t distribution also approaches 1 as the value of t becomes much greater than 0. The student's t distribution differs from the standard normal distribution because the shape of the student's t distribution is also a function of the sample size. The student's t distribution shown has a sample size of 100. The parameter used to determine the value of t is called the degrees of freedom. This value is always 1 less than the sample size, and for this example has a value of 99. As the degrees of freedom decrease from 99, the shape of the student's t distribution changes. Note that the maximum value is decreasing, but the tails are flaring higher. This implies the area under the distribution in the center is becoming less, as the area under the tails become greater. The cumulative distribution shows that the total area under the student's t distribution still approaches 1. As with the standard normal distribution, the total area under the student's t distribution is also 1. And this is also demonstrated by the cumulative distribution of each. Note, as the degrees of freedom increases, the shape of the student's t distribution approaches but never exactly equals the shape of the standard normal distribution. Let's now see how we determine the value of t for a given area. This is the chart from which we determine the value of t for a given area under the student's t distribution. The 3 highlighted rows on the top represent the area we are dealing with for the problem at hand. The top row is labeled one-tail area, and is the area under the student's t distribution for one tail. The second row is labeled two-tail area, and is the area under the student's t distribution for 2 tails. The third row is labeled df for degrees of freedom and c for confidence interval. The df is the column under this label, and the c, confidence interval, is the row to the right. Notice that 2-tail area is always twice what the 1-tail area is, and the sum of the 2-tail area and confidence interval is always 1. We will better understand this after we do a simple example. Let's say we are looking for a 98% confidence interval. This means that we are looking for a t-value that has 98% of the total area of the t distribution between them, or 2% of the area in 2 tails, or 1% in each tail. Notice that given the 98% confidence interval we are looking for, requires the remaining 2% be the area of 2 tails, and 1% be the area in each tail, are actually the same criteria and lead us to the same column. The row we use is determined by the degrees of freedom. For example's sake, let's say that the sample size is 20, making the degrees of freedom equal to 19. from the degrees of freedom equal to 19 and the area of two tails equal to 0.02, we find the value of t equals to 2.539. We need to point out here that this represents the absolute value of t. It represents minus 2.539 for the limit on the left and 2.539 for the limit on the right. Notice that as the degrees of freedom changes, the value of t changes also. This is not because the area in the tails is changing, it is because the shape of the student's t distribution is changing. So let's review what we just did. We have a student's t distribution, and we wish to find a confidence interval of 98%, which means that there must be 2% of the total area in the tails. With a degree of freedom of 19, the t-score that makes this division of the student's t distribution is plus or minus 2.539. The shaded area on the left and right are each 1% of the area. Let's now superimpose the standard normal distribution onto the same chart and determine the equivalent z-scores for a 98% confidence interval. We need to find a z-score that has an area of 0.01 to its left, but the best we can do is 0.0099. The z-score that has this area to its left is minus 2.33. Switching to the positive z-score table, we now need to find a z-score with an area of 0.99 to its left. And here the best we can do is 0.9901. The z-score has a value of 2.33. So the same interval under the standard normal distribution has a z-score of plus or minus 2.33 and is represented by the shaded area under the standard normal distribution shown here and here. The confidence interval we determined for the standard normal distribution is represented here, and the confidence interval we determined for the student's t distribution is represented here. Notice that the interval for the standard normal distribution is smaller. This makes it clear that knowing the standard deviation of the population is always an advantage in determining a confidence interval, and is even more so if the degrees of freedom is small. We will demonstrate this again in later videos where the standard deviation of the population is unknown.